In this video, we're going to learn more about functions by talking specifically about inverse functions. But in order to have an inverse function, we first have to learn about a one-to-one function. So let's start with that definition. A function f is called a one-to-one function if for every a and b in the domain of f, if a is not equal to b, then f of a is not equal to f of b. And a different way of saying this, so equivalently, if f of a is equal to f of b, then a has to equal b. So remember when we first learned about functions and the difference between a relation and a function, we talked about how we can't have repeating x values. You can't have the same x value going to a different y value. Now, a one-to-one function extends that, and now we can't have repeating y values either. So every single x goes to a unique y, and every single y has a unique x going to it. You can't have repeats. One way to see if you have a one-to-one function is to use something called the horizontal line test, which is kind of like our vertical line test. So the horizontal line test just tells us that f of x is a one-to-one function, which I'm going to start abbreviating as just 1-1 for one-to-one function, if no horizontal line intersects the graph of f in more than one point. So remember, we used to use the vertical line test to figure out if something was a function. If a vertical line hits the graph more than once, you don't even have a function. Now this is saying, on top of that, if a horizontal line touches the graph more than once, then it's not one-to-one. It could still be a function, it just won't be a one-to-one function. So let's do a bunch of examples figuring out if a function is one-to-one. We're going to use the definition sometimes, and we're going to use the horizontal line test other times. So a bunch of examples. Is the function one-to-one? And our first one is going to be h is equal to 4, -5, 6, 1, 2, 4, and 0, -3. Is this, well, first we should check, is this a function? And then we should check, is it one-to-one? So a way we can do that pretty easily is write down all the x values on one side and all the y values on the other side. And draw arrows showing the relation between these. Now, this is a function if all of our x values only go to one place. And we can see that all of my x values only have one arrow coming out of them. So this is a function. To see if it's one-to-one, you have to check to make sure that there's only one arrow coming into the y values. And that's the case too. I don't have two x's going to the same y. So yes, this is a one-to-one function. Let's do another one similar to this. Let's look at 1, 0, 3, 0, 4, -5. Is this a one-to-one function? And I'm going to do it the same way. Write down all my x values, write down all my y values, and draw arrows showing the relationship. First, is this a function? Yes, it's a function because I don't have an x value going to 2 different y values. Is this a one-to-one function? No, because this y value here of 0 has 2 different x values mapping to it. So this is a function, but not one-to-one because of the repeating y value of 0. How about using a graph? Is the graph is this graph a one-to-one function? Well, since we have a graph, we can use the vertical line test to make sure it's a function and the horizontal line test to check to see if it's one-to-one. Now, for vertical line tests, you can see if I draw vertical lines anywhere, we're only going to have one point that it touches, so it is a function. But if I look at the horizontal line test, here's just one example of a horizontal line. It's hitting my graph in 2 different places, so that means it does not pass the horizontal line test. It is not one-to-one. Let's do another one using the graph. Is this the graph of a one-to-one function? Well, some of you might right away say, yes, it absolutely is. It passes the horizontal line test, so we're good to go. However, this does not pass the vertical line test. For example, here's a vertical line that hits in 2 places. So this graph here is not even a function. Which means, of course, that it's not a one-to-one function. Even though it passes the horizontal line test, it's not a one-to-one function because it's not even a function. So you have to make sure it's a function first and then check with the horizontal line test if you already determined it was a function. One last example using a graph. Is this the graph of a one-to-one function? First, check, is it a function? To check if it's a function, remember you're going to use the vertical line test. Ensure that every single vertical line can only hit in one place. This is a function. Is it one-to-one? That's when you use the horizontal line test. And I'm going to draw a few of those because that's our new test. Here's a few horizontal lines, checking my horizontal line test. And you can see each horizontal line is only hitting one time. So it passes the horizontal line test, so yes, it's one-to-one. So far we've been able to figure out if a function's one-to-one or not by using just, when we have a list of points, using our definition, or using the horizontal line test when we have a graph. But what if they give you an equation? I mean, you could always just graph the equation and then use the horizontal line test. That's perfectly fine. But we can also use the definition just using our equation of a function. So I'm going to do a couple examples of that as well. So we were on part F. Is this a function? F of x equals negative 4x plus 1. If you wanted to, you could graph it and use that horizontal line test, but I'm going to show you how you can figure this out just using the definition of one-to-one. We are going to assume that f of a equals f of b. According to our definition, if f of a equals f of b, then a has to equal b if we have a one-to-one function. So we're going to set f of a equals f of b, write down what those things are. Negative 4a plus 1 equals negative 4b plus 1. And then we're going to see if we can get a to equal b. I'm going to subtract 1 from both sides of my equation. So I get negative 4a equals negative 4b. And if I divide by negative 4, I get a equals b. So I had f of a equals f of b, and that implies that a equals b. That means that this is one-to-one. So yes, it's one-to-one. When you do this procedure, the way you know it's not one-to-one is if you don't end up with a equals b at the end. If you end up with a equals b, you're good, and it's one-to-one. Let's do one more example like this because it's a little bit trickier. So part G. How about the function f of x equals absolute value of x minus 3? Well, to figure out if it's one-to-one or not, we're going to let f of a equal f of b and see if we end up with a equals b. F of a is absolute value of a minus 3. F of b is absolute value of b minus 3. If I add 3 to both sides, I get absolute value of a equals absolute value of b. But what does this mean? That means that a is equal to plus or minus b. For example, if a was equal to 5 and b was equal to negative 5, you would still have their absolute values equaling each other. So a does not have to equal b. It could equal negative b. So is this one-to-one? No, it's not, because I didn't get a equals b, I got a equals plus or minus b. All right, so that's all about one-to-one functions, but this video is supposed to be talking about inverse functions. So the reason we've been spending all this time on one-to-one functions is because those are the types of functions that actually have inverses. So now we're ready to define what an inverse function is. Our definition is, let f be a one-to-one function, then g is the inverse function of f, or just inverse of f, if f composed with g of x equals x for all x in the domain of g, and g of f of x equals x for all x in the domain of f. So what this is saying is two functions are inverses of each other if when you compose them together in either direction, you get just x as the result of the composition. You do have to check both compositions because sometimes you'll get x for one of them, but not get x for the other one. However, if you're checking using composition and your first check gets something not equal to x, you don't need to check the other one. This says that it's going to be an inverse only when both of the compositions are equal to x. So if you get one not equaling x, you already know it's not the inverse without even checking the other composition. Little bit of notation. The inverse function g is often denoted by f with a little -1 of x. That is pronounced f inverse of x, so that's the notation we use to indicate an inverse function. So now we need to do some examples checking to see if we have inverse functions. So are these functions inverses? I have f of x equals x plus 6 over 2, and g of x equals 2 times x minus 6. So to check if these are inverses of each other, we have to check f of g and g of f. I'm just going to start with f of g. So f of g of x is the same thing as f with g of x plugged into it. So this means I'm going to take my function g, which is 2 times x minus 6, and plug that into my function f. So my function f was x plus 6 over 2. So my f of 2 times x minus 6 is equal to 2 times x minus 6 plus 6 over 2. Remember that when you're doing composition, what we're doing here is taking this entire function, 2 times x minus 6, and replacing all of my x's in the other function with that expression. So now I just have to simplify this to see if I get x. I can distribute to get 2x minus 12 plus 6 over 2. And then I combine like terms on the top to get 2x minus 6 over 2. I can simplify this if I factor a 2 out of the top. 2 times x minus 3, all divided by 2, because now I can cancel out those 2's and I get x minus 3. So are these inverses of each other? No. They are inverses only when you get x for the compositions. And I got x minus 3, not just x. So these are not inverses. And I don't even need to check the other composition because I already know they're not inverses from this first composition. Let's do another one. We're going to find out if m, which is 5 over x minus 2, and n, which is 2x plus 5 over x, we're going to find out if these are inverses of each other. And again, to do that, we have to check the composition. I'm going to start with m of n, which remember is m with n of x plugged into it. Which means I'm going to be plugging in 2x plus 5 over 2x plus 5 over x for all of the x's in my function m. So I'm going to have 5 on the top. Instead of that x, I'm going to have 2x plus 5 over x, and then I have a minus 2. So now I have to see how to simplify this. What I would do is I would rewrite the denominator all as one fraction down there. So I need to rewrite this 2 as 2x over x so that I can combine those together. So I have 5 over 2x plus 5 over x minus 2x over x. First, notice this is still the same exact thing. I'm just writing these with a common denominator so I can write them together. Now when I subtract those, I'm going to have 2x plus 5 minus 2x, which is just 5, over x. So now I'm dividing by a fraction. We know when you divide by a fraction, it's the same as multiplying by the reciprocal. So I'm going to rewrite this as 5 times the reciprocal of my denominator, which is x over 5. Now my 5's will get to cancel out, and I just get x. So we found out so far that m composed with n is x. Does that mean that they're inverses? Not necessarily. It just means that we don't know for sure that they're not inverses yet. We have to check the other composition. If I check the other composition and I also get x, then they're inverses. So far, it's possible. They might be inverses of each other. To check the other composition, n of m, we have to plug m of x into the function n. Now my m of x was 5 over x minus 2. So that's what I'm plugging in to my other function n. My function n, remember, was 2x plus 5 over x. So I'm going to have 2 times something plus 5 over that same thing. The thing that's being plugged in for x is 5 over x minus 2. So I have all of that. Now, I am going to end up multiplying by this reciprocal. First thing I'm going to do, though, is take care of this multiplication here so it looks a little easier. 2 times this 5 over x minus 2 is 10 over x minus 2. So what I get is 10 over x minus 2 plus 5 all over 5 over x minus 2. That's a little smushed down there. I'll actually rewrite it on the top so it's not as smushed. What we just had was 10 over x minus 2 plus 5, all divided by 5 over x minus 2. And now I'm going to rewrite this as multiplying by the reciprocal. So I'm going to have in parentheses 10 over x minus 2 plus 5 times the reciprocal, x minus 2 over 5. That gets to be distributed. When I multiply that x minus 2 over 5 times the 10 over x minus 2, the x minus 2's cancel out, and I just have 10 over 5, which is 2. And now when I multiply this x minus 2 over 5 times the 5, my 5's get to cancel out, and I just have x minus 2 left. So 2 plus x minus 2 is x. So this tells me I did the composition both ways, and I got x both times. This means that the functions are inverses of each other. All right, so now we've learned how to identify one-to-one functions by looking at a list of points, by using the horizontal line test, by just using the definition when we have an equation. And we've also learned how to verify two functions are inverses by using function composition. What we don't know yet is how to find the inverse of a function when we only know the function itself. And that's what we're going to learn now to finish up this video. So, how to find the inverse? We have a whole procedure for it. The procedure to find the inverse function. First, replace f of x by y. Then, interchange x and y. Then solve for y. And very last step is replace y with f inverse of x. So our procedure is to first rewrite this with a y instead of an f of x. Then we're going to flip-flop all of our x's and y's, solve that new version of the equation for y, and rewrite it as f inverse. It sounds like a lot of steps, but it really isn't too bad once you learn how to do it. So let's do a couple examples of this. All right. Find the inverse of f of x equals 4x plus 3. All right, well, to figure out the inverse, the first step is to rewrite this with a y instead of an f of x. So I get y equals 4x plus 3. Step number 2 is to interchange my x and my y. So I'll get x equals 4y plus 3. Step number 3 is solve for y. So I want to get y by itself. So I'm going to subtract 3 from both sides. And then I'm going to divide by 4. So I get x minus 3 over 4 is equal to y. And then my last step is to rewrite this with an f inverse instead of a y. I'm going to put it on the left side. F inverse of x is equal to x minus 3 over 4. And that's all there is to it. Some problems are a little bit more complicated because we have complicated domains and ranges, but a lot of the functions are very straightforward like this. Do another one. Find the inverse of f of x equals x minus 2 over x plus 2. Okay, well, our procedure for finding the inverse is to first write it with a y. Then my next step is to interchange my x's and my y's. So I get x equals y minus 2 over y plus 2. And now I have to solve this for y. So I'm going to multiply both sides by my denominator. So I'm going to get x times y plus 2 equals y minus 2. And now I can distribute. X times y plus 2x equals y minus 2. Still don't have y by itself, but we're getting closer. I want to get everything with a y on one side and everything without a y on the other side. So I'm going to move all the terms with a y to the left. So I'm going to subtract y from both sides. And now I'm going to move this 2x over to the other side. I get xy minus y equals negative 2x minus 2. Still don't have y by itself, but I am close. All I have to do is factor out a y. So I have x minus 1. And now I can divide both sides by x minus 1 to get the answer. And I get y equals negative 2x minus 2 over x minus 1. And then all I have to do to finish my problem is rewrite this as f inverse of x equals negative 2x minus 2 over x minus 1. And that's my inverse function. Now, one thing that's very important to know about inverse functions, you see how our x's and y's flip-flopped? That also means our domain and range is flip-flopped. So the domain of f is the same thing as the range of f inverse. And the range of f is the same thing as the domain of f inverse. So that's something very important to note. Sometimes we don't have domain and range equal to all real numbers, and you'll have to keep track of this. So an example like that where we're going to have to keep track is something like this. Find the inverse of n of x equals x squared plus 1, where x is less than or equal to 0. So this right here, x less than or equal to 0, is telling us our domain is not all real numbers. The reason for that is because if I had it as all real numbers, this wouldn't be a one-to-one function, so I wouldn't be able to find an inverse. So I'm restricting it to just this for my domain. I would start by finding my domain of my n of x, which we already know. X is less than or equal to 0. What would be the range of n of x? Well, let's think about what this graph would look like. X squared is just a parabola, but we're only taking half of it. We're taking the left side of the parabola. And then we're shifting it up one spot. So my original graph would look like this parabola, but since I'm only using x less than or equal to 0, we're only looking at this left side of the graph. The range of that starts at 1 and goes all the way up to infinity. So it's y is greater than or equal to 1. So when I find the inverse of this function, the domain of my inverse is going to be x is greater than or equal to 1. And the range is going to be y is less than or equal to 0, because the x's and y's flip-flop. So I'm already going to write down domain of n inverse, even though I don't know what it is yet, is x greater than or equal to 1. And the range is going to be y is less than or equal to 0, just because these are flip-flopped of each other. Now we're ready to find the inverse. I'm going to rewrite my function with a y instead of n of x. I get y equals x squared plus 1. Then I flip-flop my x's and y's. And now I need to solve this for my y. So I'm going to subtract 1 and then take a square root. And it would normally be plus or minus the square root. However, this is why we took our time to figure this out first. The range is supposed to be only negative things. Y is less than or equal to 0. So I only am going to want the negative square root. Y is equal to the negative square root of x minus 1, so that it matches the range that I'm supposed to get. This means that my inverse function, n inverse of x, is equal to the negative square root of x minus 1, and it has our domain that we found earlier, that x is going to be greater than or equal to 1. So when you have to find an inverse function and you have a domain that's not all real numbers, it helps to find your domain and range of your original function and flip-flop them to find the domain and range of the inverse function before you even try to find the inverse. Then it helps you figure out the answer. Let's do just one more. Find the inverse of g of x equals the square root of x plus 2. Now, my domain of this particular function is not given to me in the problem, but I know the domain of a square root is not all real numbers. So I'm just going to go ahead and find my domain and range first. My domain, remember, we need things underneath this square root to be greater than or equal to 0. So my domain is x is greater than or equal to negative 2. And what is the range of g? Well, think about what the graph looks like. We have square root of x that looks like this, and then I'm adding 2 to my x, which is a shift to the left 2 spots. So my graph looks something like that. Regardless, the range starts at 0 and goes up forever. So my range is y is greater than or equal to 0. So now we can figure out what the domain and range of the inverse function will be before I even find the inverse function. My domain of g inverse I get by looking at the range of g. I had y is greater than or equal to 0, so my domain of g inverse is x is greater than or equal to 0. My range of g inverse I get by looking at the domain of g. I had x is greater than or equal to negative 2, so I'm going to have y is greater than or equal to negative 2 for that range. All right, so now let's go ahead and find that inverse. We need to rewrite our function g using a y. So I get y equals the square root of x plus 2. Then we flip-flop our x's and y's. And now I need to solve this equation for y. To undo this square root, I'm going to need to square both sides. So I get x squared equals y plus 2. And then to get y by itself, we just subtract 2. So I get x squared minus 2. That means my inverse function is x squared minus 2, but I have a domain of x is greater than or equal to 0. And that's all there is to it. So that's about it for inverse functions for this video. Right after you learn about inverse functions, the most common thing to learn about is exponential functions and logarithmic functions, because they're inverses of each other. And that's exactly what we're going to do here too. Our next video is going to be about exponential functions, and the one after that's about logarithmic functions, because those are great examples of inverse functions. So I hope you stay tuned for those. If you have any questions, drop them below, or if you're a current student, come to office hours or email me, and I'm more than happy to help you. I'll see you for our next video on exponential functions.